Hello and welcome to today's Wolfram Institute live stream. Today we're joined with Joseph Natal, a doctor or student at
It's,
Karlsruhe Institute for Technology in Germany, studying laser plasma acceleration and working on the future circular collider there. Today he'll be talking about a defense for finitism in the philosophy of physics. Joseph, go ahead.
yes. Thank you, Dugan. Yes, thank you to the Wolfram Institute for allowing me to speak here. So, yeah, it's sort of a defense of finitism, but the tongue-in-cheek title is Did God make Boolean algebra, right? So it's kind of like um, a framework that I want to sort of have corroborate with the Wolfram physics and in particular Wolfram's philosophy. So what are your sort of assumptions about the continuum and the infinite, right? When you perform mathematical calculations in undergraduate or high school, right? You sort of taught about limits and the infinite. But what I want to claim, and what hopefully is compatible with Wolfram physics, is that the continuum and infinite are superfluous for mathematical physics. And I would argue in both theory and practice. So maybe you think this is on the face of it kind of absurd or trivial, but I'm hoping to nudge you in the direction that it's true. So sort of as an appetizer, this sort of hors d'oeuvres here, um, I sort of proposed in the center column a thesis and then the sort of finite antithesis of the thesis. So, you know, back in the time of Euclid, he sort of invokes the infinite when he talks about the indefinite extension of parallel lines, right? So this is one of his axioms of geometry. And the antithesis in this case is sort of just a small angle approximation, right? It's sort of like the floating point version of this, where you can never truly reach the platonic the platonic ideal of the parallel, right? So in calculus, you have limits, but in practice on computers, computationally, it's usually implemented using finite difference methods. And there are also other formulations of calculus that, to varying degrees of crackpottery, sort of reformulate the calculus without actually using limits or the infinite. So yeah, I would recommend to maybe look at those if you're curious, but perhaps the most popular example of where sort of the infinite causes problems, so to speak, is in quantum field theory, right? So the idea of renormalization, where we take these sort of singularities, these infinities, and we sort of sweep them under the rug, so to speak, right? So the antithesis of that is simply, truncating your model or not having it diverge. But we'll get into a little bit more detail with that later. So those are sort of some examples, and don't take my word for it, right? Or perhaps you've heard of the criticisms of this idea of renormalization, where here we can see from the Wikipedia, Dirac and Feynman also sort of think that this is nonsense, right? So we sort of have a criticism here where Feynman says, it's not mathematically legitimate, right? So is this a problem with the theory itself, or the way we think about the theory, or what, right? So is there any practical problem that must invoke the infinite or infinitesimal? So for more examples, right, we thought that the proton was fundamental until it wasn't. So what does this mean for the singularity of the Coulomb potential? So nominally, I think the proton is made up of 3 quarks, but in my undergraduate, I learned that no, in fact, it's not made up of 3 quarks. It's actually kind of a soup of these subatomic particles, right? So you can't necessarily model it with this potential that goes to infinity as you reach the particle. And then in calculus, many Taylor series have simple combinatorial interpretations, right? So you don't necessarily need to use the idea of limits in these in the calculus, I believe, right? So for example, if you Taylor expand any function, you could get something that has a combinatorial interpretation, such as, the number of partitions of a set of n elements. And this is a whole field called generating functions, which is, I think there was a very good textbook written in 1990. If you're interested in that, perhaps you're familiar with that, but it's what makes it less powerful than other definitions. And then, of course, it kind of goes without saying, in quantum mechanics, we sort of overturn the continuum mechanics with discreteness. So the energy levels are discrete in an atom, right? And so here's an example, a visual example, where I show sort of a table of these coefficients that are relevant for the hydrogen atom. And it's kind of like we're resorting back to something like a lookup table instead of performing all these integrals and using this continuum 18th century mathematics, right? And I think this kind of hints towards a more discrete future of mathematics, or at least that's what I would like. So there's also beauty without the continuum, if that hasn't sort of convinced you. One area of research that I like to study is strongly regular graphs, which maybe is kind of something similar to what Dugan worked on in some ways, because you kind of have these highly symmetric graphs, right? These graphs have all the vertices have the same degree, and there's a particular constraint on the number of common neighbors that each vertex has to other vertices. And so you kind of get these wild, but usually beautifully symmetric structures. And the late John Conway, this was an area of his research. So there's sort of a problem from 1969, and John Conway sort of compiled a list of 10 problems that are very much in the style of John Conway, where there's sort of unsolved problems about combinatorial structures or combinatorial games, right? They're almost childlike in their simplicity, but they're unsolved. And there's a problem about a strongly regular graph that I've had a keen interest in. So another example is, of course, Wolfram's simplest axiom, right? So this used an automated theorem prover, and I'm sure, I know, James, I think I saw a post where you sort of were able to run this proof. I haven't done that yet, but maybe I should. I think it might be instructive. But so it's sort of an example of a beautiful discrete thing that just sort of emerged, right? And so it goes without saying that cellular automata are another example. The Boolean Pythagorean triples problem, which is of interest to me, it's sort of a massive combinatorial problem that was solved using SAT solver in 2016. And I also include here the discovery of the Higgs boson. Now, why do I do this? Because at the LHC, there are all sorts of events. You're essentially tracking events through these silicon detectors, or particle detectors. And a lot of that is sort of big data analysis, floating point, using your computer arithmetic. And I would describe this as very sort of discrete in nature. So it's sort of like, I guess it's an open question of, will we have another calculus where we can sort of use the continuum in our mathematics, or are we going to sort of need an infracalculus, right, which is an active Wolfram project? So what happens when we sort of zoom in, right? It's kind of a funny caricature here, but if you think about it, over the course of history, we've gone to 10 to the minus 1 meters, and we said there are 4 elements, and then we discovered the periodic table, and then finally we have the standard model, right? Now these numbers might be kind of, yeah, I don't know the error bar on these numbers, but I expect you could create something like a Moore's law, right? When it comes to how small we can we can look at, right, if you guys are familiar with the sort of videos of molecules that have been coming out in recent years, maybe that's decades old now, but will it be the case that, at the bottom, that's something, I think Stephen might have to correct me on this, it might be at 10 to the minus 100, but you kind of get the idea, if we probe further, will we find sort of the elementary elements and their relations? What technology would bring this about, right? Okay, so now I'm going to sort of go off into some of the history, some of the philosophical thinkers. So Kronecker, famous mathematician, he was sort of in my camp here. We're very finitist here. So he said that natural numbers were created by God. Everything else is the work of men. But I would like to, override that here for a second and claim that binary is actually the most fundamental thing, if that's not obvious to you, right? So in Leibniz's view, binary numbers represented a fundamental form of creation, reflecting the simplicity and unity of the divine. And I had no idea that Leibniz, one of the inventors of calculus, also had some notebook scribblings, right, in binary here. And I don't do it justice, but there's an entire book here on Leibniz on binary, the invention of modern computer arithmetic. So you could read that book for more information. So what are each of these? So you might say maybe it's a cellular automata. Maybe this one has 3 colors, right? But in fact, the top row I think is the number 5, the middle row is 7, and the bottom row is 12, right? So this is just sort of to illustrate that undergirding all of our math here, addition can be done in base 2 and is effectively a nonlinear cellular automaton. That's how it's behaving on our chips, right? So here's the equation for a simple adder in binary, right? So I think you might need another row here for the carry bit, but that's sort of besides the point. So do numbers simulate Boolean algebra, or does Boolean algebra simulate numbers? And maybe you could argue as an objection that perhaps this is just fashionable because we're so enmeshed with our computer technology. And I think I could give this some credence. But there are people, that this is a study from 2011 where they don't necessarily think about numbers in the same way that we do. Right. So in here, here's a quote that they don't consistently extend the correct number of fingers when communicating about sets greater than 3, right? So because there's simply no purpose, right? These are indigenous people, and they don't necessarily need to invoke these numbers in their particular, right? So, but I feel like you would be very hard pressed to find a people without yes, no, or and, right? So these sort of more fundamental drilling down, these fundamental operators that we use in logic. And then you could also argue that perhaps this is pedantic or just a sort of a reframing, but I think even so, there's still something to be said about the reframing. I think there's a significance to the verbiage and the language that we use when we talk about our mathematical tools. So, calculus, for example, works, right? There's an unreasonable effectiveness of mathematics. I guess I'll put work in air quotes there. So but then, to sort of relate it back to the Wolfram project, what is infracalculus and infrageometry about? What is driving the dissatisfaction with current models of mathematics? Or, is everything sort of encompassed in a category theory or a graph theory? So I hope they don't mind here, but I screenshotted some clips from a live science that's done at Wolfram. That was done at the Wolfram Institute here. So then what is the machine code of Boolean algebra? Here's the first maybe several trivial functions using the standard basis of and, or, and not on 2 variables. Is it just an arrangement of symbols that transform according to fixed rules? A formalization of our sort of human experience of and or not? Perhaps both. And this is going to sort of go into the opinion section here, but I think the rules of logic are sort of unique, transcendent, fundamental, and atemporal in some sense, right? You think about time and memory, and I think there's actually something more ontological about the rules of logic themselves. And this, of course, isn't new. But I think the bits in hardware that are on or off are sort of a microcosm of this more formal truth, right? And I think this is sort of, Wolfram would perhaps say the same thing with regards to the Roolead. Right? So, but to get back just quickly to the experimental evidence for the atoms of existence, I also make some conjectures here. I think it will be sort of discrete, right? I think the signs will show that the experimental evidence will, of course, be discrete, right? Almost by necessity due to the fact that we use detectors. It will be incomplete. I think there will still be wanting, especially in the philosophical domain. And it will be sort of rare, but still accessible for wide mimetic propagation, right? So you kind of have to talk about how ideas in science spread. And right, if you're too stuck into an ivory tower, or you have your own theory of everything, but yet somehow it doesn't transmit past layers of communication, then I think it won't generally be successful, right? So I am personally biased toward the study of physics of plasmas on Earth. I know there are maybe astrophysical plasmas that are very interesting. This is just one avenue, but I think this area is sort of exciting. So to sort of wrap things up here, so Cantor was famous for introducing the idea of infinite sets in mathematics, right? And Hilbert also kind of built on this. So David Hilbert, the famous mathematician, says, "From the paradise that Cantor created for us, no one shall be able to expel us." But I simply disagree. And there were also others who disagreed, including this guy Frege. There's sort of a controversy, sort of a famous controversy. And here's a little poem: "Abstractions might, a boon is found, while man does keep it tamed and bound. Awful its heavenly powers become, when that it stops and stays are gone." And I think this was attributed to Frege, who sort of rivaled Hilbert in his ideas about these infinite sets, for example, and sort of the axioms of set theory and these sorts of things. But I wasn't actually able to really attribute it to Frege here. So this is sort of it's myself questionably citing Frege here. So I'll take the claim for this. And in the sort of appendix there, you sort of hear some other thinkers and how they thought about metamathematics. So here's another thinker named Brewer, who sort of had this creating subject, so to speak, which was his sort of axiom for, like, it sort of produced his axiom system for mathematics. It's very kind of curious. And then even back to Plato's Parmenides, you can see he's almost doing releology here. So he's sort of enumerating all of these possible ontological states here in a very interesting way. So he's saying the one is not itself, and the one is nowhere, and the one is not in motion. And then Gödel has sort of this curious God's theorem where he proves the existence of God in this one page. So I don't know, maybe that wasn't a great concluding slide here, but that was pretty much all I wanted to present. So thank you for your attention.
Yeah, thank you.
Very cool.
Hopefully it wasn't too fast, or I feel like I was sort of fire hosing.
There's a slide about beauty. I just have a question
Beauty.
on the, yeah, can, I don't, I sort of have, I mean, sort of have this notion that beauty can be attributed to symmetry. And do
Yeah.
you think, if you think about the first figure, is sort of symmetrical in nature? And
Yeah.
what about the equations? Like, how do you think about beauty in terms of equations?
Yeah.
Um,
Yeah,
for
that's a really
example,
good point.
the Wolfram's simple axiom, it's hard to identify how beauty relates to that, right?
Yeah, I mean, I guess the beauty is maybe the simplicity and the oneness of the axiom itself, right? So despite the fact that the proof goes all hairy and the proof graph is very messy, right? There's still it's sort of cool and unique. And maybe there's symmetric structure in the axiom itself a little bit, right? If you squint. But I would say that maybe it's within the uniqueness and the oneness of the axiom. Personal opinion, right? I guess you could say beauty is in the eye of the beholder too.
Yeah, certainly those regular graphs are very beautiful. I mean, they remind me of edge graphs for regular polytopes, especially like
Yeah,
I worked a lot with the E8 polytope.
yeah,
Yeah,
yeah. E8. I feel like I've seen that before. Is that
right.
in physics too? Do you know?
It's used in gauge symmetry physics. So gauge
Yeah.
symmetries is you have like a set of um, symmetries on the sort of gauges that you have in the standard model, the quantities involved, and these are often encoded as sort of like a geometric symmetry.
Hmm.
And it turns out that the set of the geometric symmetries can be boiled down into components, the prime components. There are finitely many types of different finite geometric symmetric components. And
Hmm.
E8 is like sort of the largest of the exceptional type. So it's
That's cool.
uh, kind of not surprising that a gauge symmetry would fit inside of a very large symmetric set.
Yeah. Have there been like a graph of I think there's probably a graph associated with the E8. Is that right too? Like, could you associate it with a graph, I think?
Well, the
Not sure.
as a geometric construct, the E8 polytope does have a graph structure for its vertex and edges.
Mhm. Yeah, okay, I see what you're saying. The translation from a polytope into a graph by yeah. I guess the neighboring what is it? Neighboring faces or neighboring edges would be literally the edges of the graph. Because when I think of a polytope, right, I'm thinking about a convex hole and all this.
Yeah, exactly. So
Yeah.
the root polytope for the E8 lattice is the E8
Mhm.
polytope, and
Mm,
it's kind of like a platonic solid in the sense that it's highly regular. Um,
cool. Yeah, I need to look into that niche a bit more.
yeah, it's fun.
Um,
It's really cool. Yeah, so there's something like really primal about like Boolean algebra, Boolean logic, um,
right. Yeah.
and it ties into base two arithmetic, because you just have like on or off, zero or one, true or false, and the
Yeah.
sort of connective operations on that.
Yeah. And it's kind of related to like how simple can you go, right? Like I think Stephen had something about what is the simplest Turing complete CA or something along these lines. And I don't remember if it required or Turing complete Turing machine wait,
It's Turing complete.
something
Yeah,
yeah.
Rule 110, I believe. Um,
We're
you
on
can-
10, but I think there was another problem, something about finding the simplest, if it might have been a certain 3-color CA and determining whether it was universal. But yeah, I mean, it's kind of related, yeah. Insofar as it's like asking the question, how simple can you go? How condensed can you make something? If you just have these 3 operations and or not, and you transform them, what can you create? And
I often
how
like to
how
say that
quickly?
um, if you can have a system, a symbolic system that emulates a certain phenomenon, if you make that system as simple as possible, then you've like boiled down the essence of that phenomenon.
Right. Right. Yeah, because you could always invent sort of faster, like you could use real numbers or natural numbers, but can you do it with bits? Right. I don't think the answer is yes, both philosophically and practically, but maybe it's like impractical sometimes. So I don't know, maybe a bit heady, right? So I feel like once you get into the philosophy, it's always difficult to make definite statements. But
I wonder what you think about there's a statement in I think it's in the next slide. So unreasonable effectiveness of
yeah.
mathematics, and I wonder what you think about that statement, and is it
Yeah.
relating to the do you think that math is fundamental to everything, including the rheology or R'Lyeh?
Yeah. Yeah. I mean, I think, yeah, a lot of experimental mathematics is just rheology in its essence. Um, and I think, once you start talking about unreasonable effectiveness, you have to ask the question, effective at doing what? So we sort of make we can make 100 new problems for each problem that we solve. So it's kind of a question about, that's why I kind of like the idea of games in mathematics. This is what John Conway liked a lot as well. And to some extent, cellular automata are kind of game-like, I guess. Yeah, I mean, I think there is an unreasonable effectiveness of mathematics, but I think it can be sort of, yeah, described as rheology and condensed down to something like a graph, like a hypergraph, which is why I sort of follow the Wolfram physics ideas, or at least, yeah, it could be distilled, let's say.
Yeah, like a graph has distinct components and then connections between them or interactions between them. Speaking to the effectiveness of mathematics, I like to think about the fact that our physical world, right? You think about like integers, it's discrete, different quantities, right? In our world, we have like um, solid objects and numerous of them.
Right, which is non-trivial. This philosophically non-trivial statement you made there, but yeah.
Right.
Yeah.
And we live in a universe that has like object permanence. That things just don't like fluctuate in and out of existence. You have this rock and that rock, and you have 2 rocks. You open a box, you put 2 rocks in it, close the box. You take 3 rocks, you open it, shove them in there, and now you have a certain number of rocks in there. You open the thing again later, you look and you count them, and you have like 5 rocks. So right there, it's like
are we gonna get philosophical? Because I would take objection to that statement. I think there's a probability, but it's not probability 1 that there's still gonna be 2 rocks when you open the box again.
Oh yeah. Well,
that's what quantum mechanics, right? Well, you could use quantum mechanics, I think, to make that argument, but you could probably
I
go
mean, like
beyond
even just very simply, if there's a hole in the box that you are not aware of, and that talks to computational boundedness, there's no way you can know for certain the parameters within which the system you are operating. So you put 2 rocks in the box, but you didn't realize that, when you open the box again, one of the rocks disappeared. You don't know why, but also you don't know the state of the entire universe as well. So to what degree are you encapsulating the entire state within your reasoning right now? So the
It's
object
a
permanence
philosophical
is
box.
interesting.
It's,
Yeah.
It's a lockbox, as Al Gore would say. But
yeah, but exactly, so that's the point. So now that it's a philosophical box, by definition, you're encapsulating the entire state of every possibility of that system. That is not easily done in reality. And that's the distinction. So there's object permanence theoretically, yes.
In a lot of ways, there's, conservation of matter and energy exhibited in our universe. And I think that's we should be so lucky.
So that's a little bit different.
Yeah.
So that's like a physics law, which is sometimes difficult to abstract all the way to a rock, because a rock is such a computationally irreducible combination and complex combination of those physical laws that it's difficult to make such a wrought statement that it is permanent. You could say that there's like conservation of energy, and that's a very simple, minimal foundational statement that applies to various things, but at a given level of boundedness. By the time you get up to the concept of like a particle or a rock, I think there's very few statements that you can make like fully that applies. And at the end of the day, it's also observer dependent. So yes, there is object permanence, but from whose perspective? From the rock itself, yes, probably it is permanent for its entire existence. But from the perspective of you, who's on the outside of that box, that's in reality impossible to always define every possible thing that box does and does not have. I think from your perspective of that outside observer, I think it's difficult to say that those rocks are going to permanently be there.
Well, in the span of like 10 minutes or something. I mean, let's just maybe give me like a little slack here, but I'm in contrast. Okay, so you put rocks in the box, you open it, close it, you put more in, you count them at the end, and you might have like 2, 3 later, and 5 total at the end, right? So it's like you have this arithmetic of numbers, and then this like calculus of keeping track of how many rocks you have, or objects, and distinct objects. And in that sense, as long as everything goes smoothly, the integer arithmetic will be effective in maintaining the quantities of solid objects you have. If, on the other hand, we were entities that lived in like a nebula out there in space, just like amorphous blobs floating around without like clear physical boundaries and without like clear like independent identities, and there were no like objects that were like distinct from each other, then like having integer arithmetic or conceiving of like the arithmetic of integers wouldn't be effective way of keeping track of anything in that sort of world. I would say.
But then wouldn't you have to just sort of resort to a oneness, a transcendent oneness, like if you, because once you start saying my amorphous blob is different than your amorphous blob, but we're both somehow amorphous blobs, right? You're doing counting, but you kind of fall back on the idea of counting, don't you?
Right. So like if you can separate your own thought space from
thought space, so
your mental identity, say, okay, well, I'm like at least one consciousness floating around, and there are other consciousnesses around me, and I can communicate with them. But I was trying to push. I was even trying to like lead that into like, oh, if you get near each other, then like you kind of share thoughts and kind of share consciousness. And so you don't really have the idea of one to begin with, let's say. But let's say like some piece of that entity started like conceptualizing about like, oh, this integer arithmetic where like these integers are distinct and you have these quantities and you could add them together, and they would have like pushback against their peers or something like this, saying like, that's not really useful, is it? Thinking about integers and addition.
This also relates comes back to the question of what the universal language that you can speak, for example, to communicate through thoughts, then it must mean that you have sort of the same language you understand with each other, right? So universality of language is interesting too.
Yeah. Yeah, and I would argue that language is somehow encoded in logic, in binary, like at its most distilled level, right? Because when you speak to me, I sort of take these discrete concepts and I'm able to combine them or parse them apart, you know. But yeah, I think maybe I need to talk more about think more about language at some point, you know. Because I mean I know that's all the rage now, right? It's very relevant.
Yeah.
Do you want to, while we discuss this, do you want to put a slide on an interesting visually intriguing thing so that we
let's
can
do it.
Yeah, okay, great.
Let's do this one.
Thank you.
Something for the viewers to look at.
Yeah.
Maybe we can discuss a little bit. Oh, sorry, Dugan, you want to?
Well, there's
that
a
line of thought. Yeah.
question from the audience. Brady is asking, they say they've thought that a continuum of space means there's an infinity between any 2 points. He says that doesn't make any sense to him. Thoughts on that?
I like that. I mean, I like that. And I think that is quite simply put another, you know, reasonable statement in my opinion. Because you run into the contradictions, right? I think there are many. There's even like a Wikipedia page that's like paradoxes introduced by infinity, and it's just like one after the other. And I'm not necessarily like anti-paradox, so to speak, like maybe in the strictest sense, but you do get these kind of confusing puzzles, and it's not delineated very clearly to me.
Right. I mean, mathematically, you don't even need a continuum to have like infinitely many points between any two. You just need, you know, rational numbers for that. Will get you there.
Yeah.
Yeah. But physically and ontologically, like, can space be smooth in some real sense? Like, I don't.
Yeah, I know
I can conceive of it, but I don't actually believe it. You know.
Right. That's basically my position. I just don't believe it. And I know Stephen mentioned that in the early 20th century, I think many of the physicists believed in the discrete nature of space, but it sort of fell out of favor, out of fashion as time went on.
Yeah, especially with
something I would like
the rise of relativity and like all this, you know, stuff that's based on smooth geometry, Riemannian geometry.
Mm-hmm.
So something I'd like to comment on here, because coming into the world of how physics is really done versus just being an observer to it in like a casual sense, like watching a lot of YouTube videos, it's sometimes difficult for somebody to conceptualize the difference between what physicists say when they talk about these formalisms that they do physics with versus the nature of actual reality. And sometimes the wording can be confusing, and understandably, because we use that language to think about these models in our minds. So that's all we have to describe these things. But sometimes if we talk about like a continuous space or discrete space as different models for doing physics, and then you think to yourself, well, is physics fundamentally discrete or fundamentally continuous? I like to think that it doesn't matter. The point of the formalisms, the point of the physical laws that we create is to be able to create better predictions of what happens in reality. The fact that we're using mathematics that's continuous to make accurate predictions basically doesn't say anything about the actual nature of reality. It might help with like predictions, and it might or might not be actual reality, but that's not the point. The point is we have our experiences as humans going through life, experiencing things. And it just so happens that a particular type of mathematics is unreasonably effective at creating a certain set of predictions, which might, you know, after a bit of computational work, get replaced with a new type of mathematics that's even better. But the point is, what that says about the real nature of reality, to me, doesn't really matter. Like it's a different medium with which you can communicate what's happening. So uh, for me, that was like an epiphany when I realized that physicists talk, like, for example, in quantum mechanics, you have like the many worlds interpretation. So people can have like written a lot of sci-fi or even like, I don't know, the comic book superhero movies about like these many worlds now. And then when you say like, okay, well, there's some research paper that came out that proves that the many worlds is like more possible than not. If you just listen to that language, you're like, oh shit, so there's like multiple versions of me like out there somewhere, and maybe I can interact with them, and like maybe they had different lives, like the life that I never could live, and like, or maybe like a worse version of me. And it's like interesting thought experiments, but it's just an interpretation of what the mathematics is putting out there. So the fact that the maths works when you assume that there are many worlds or many possible worlds does not mean that you're going to meet like yourself in a different dimension. So yeah, I just wanted to give that thought out there.
Yeah, that's a nice thought. Yeah, I think I agree with your sentiment there. Like it doesn't, if you're not looking, so I guess what I'm trying to do is trying to like drill down to the what is fundamental, and if you use continuum mathematics, it's like it's not like, yeah, like you said, it's not an offense or a blight against physics, but I think if you're trying to go deeper and think about the philosophy of things, maybe there exists, right, something more fundamental, and then it sort of goes beyond just mere predictions. I mean, predictions are useful in the physical world, I would argue, useful practically, so that, you know, whatever baggage comes along with the word practical. But yeah, I think I agree that it shouldn't correlate with you know, you shouldn't think that your friend, you're going to see your many worlds brother in you shouldn't extrapolate, right, with these sort of toy models.
But how do you
such as
test whether the fundamental like how do you test whether your fundamental approach is correct? I mean, you
yeah
can make an arbitrary fundamental statement,
yeah
but to what degree is that fundamentally what's going on?
yeah that's a great, yeah, then I think you're just sort of hosed, right? You're in the philosophical regime where you could make whatever axioms you'd like, right? So to be
I
honest, I
think,
don't have a
yeah, I think this is the big thing that I had to appreciate coming into it, speaking to a lot of like real physicists. And Stephen wrote a really excellent blog piece recently about this, where people have their own theories about stuff. And I think the difference is like you can come up with any theory you want. Okay. The challenge is that does it do something for us new, or does it help us in some better way than what we already have? And maybe it's just philosophically it's more interesting. Maybe that's the value. Maybe it's at some much more fundamental starting point, which is great, and it's worth exploring because of that, the benefit that has, even aesthetically. But at what point it needs to be starting to be taken serious by people whose livelihoods and careers are actually built upon the ability to make impactful statements about these things. For those people to start paying attention to it, you have to at least get close to, or like in the right direction to be able to replace what's already there, or be analogous to what's already there, or add some kind of actual real world benefit beyond aesthetics.
yeah,
So
agreed.
yeah, I just wanted to make that statement.
Yeah,
Yes,
but
it's a
just
very
by help us, you mean okay, there might be different ways of helping us. It could be that it helps us subjectively, or it helps us objectively. So I'm not sure
Yeah, so
what
subjective is
you're
great, subject, but that's like for you, it helps you. So then maybe it's a cool hobby, it helps you like pass the time. But objectively, I think is the ultimate measure. And I mean, my worldview, the way I think about it is like predictions defines everything, but that's just again, my aesthetically pleasing way to like think about and frame everything. I would love to get Gabriel to comment on this, because I think he's got some
Is he
interesting
here?
thoughts. Yes. I don't know if you know, but it's talk, yeah.
Yeah, it's a bit later here in this time zone, but yeah, I
Same.
pretty much agree with everything that James said. Yeah,
You
Thanks,
think
Gabriel.
predictions?
yeah, but also yeah, probably the physicists, or yeah, there should be more effort going into looking into discrete models, because they are, well, simpler. Yeah, like if you have these continuous models, they tend to be not so simple, and then Occam's razor will, yeah, according to that, you should prefer the discrete models in the end. But Occam's razor also doesn't predict that the universe has to be simple. It just says like you have to first of all try to find the simplest possible model, right? That's all. And then like even if you find like a really good simple model that is discrete and everything, and from which everything else emerges, it might still be that underneath this discrete model, there's something else again, which is just unobservable and could be continuous or anything, just like James said. Yeah.
Right,
Yeah,
like
this
the
concept of taking Occam's razor seriously is very interesting. Gabriel's gonna talk for us on that at some point. I'd love to dig into it then. Sorry, Dugan.
Yeah, I like this. Oh yeah, Dugan, you go.
yeah, speaking to Gabriel's point, having a discrete system and something continuous possibly lying underneath it, like the quantum mechanics was founded on the discreteness of photon size, energy levels, right? And that's coming from like a photon is generated anytime an electron is jumping between orbitals on an atom, and those orbitals are lying in discrete energy levels because of spherical harmonics. And so that's like wave modes on a sphere, just like wave modes on a string, on a continuous string, are discretized to like a harmonic series. That's a piece of a line has these harmonics on it, and so does a spherical object. Mathematically speaking, that's still true, even if that sphere and that waveform on the sphere is like continuous. Now, it doesn't have to be actually continuous. It just has to approximate something which is continuous. So it could be a discrete thing approximating these like a sphere, a waveform on a sphere. But in principle, like it's discretized into
Yeah, if you
electron orbitals because of spherical harmonics. At least for the hydrogen
Yeah, sure.
atom, and then molecules are more complicated.
Yeah, I can flick back and forth between discrete and continuous multiple times. I mean, you can at the top you could have something discrete, and then underneath it emerges from something continuous, which emerges from something discrete underneath that, which emerges from something continuous again underneath that, and it can just go back and forth like this many times, right? In principle.
Yeah, and then that's the thing. Like, Stephen has asked, is there an experiment that would show that there is discrete at the bottom? Why do I believe that it is discrete? Maybe that's just sort of like a positive disposition towards the like understandability. Maybe that is, I think Occam's razor, like you said, would probably bias towards the discrete. But I don't have too much evidence, but besides that, right?
Yeah, I also suspect that based on what I've seen so far on simple models that exist, I also suspect that like the ultimate theory of fundamental physics that people will find eventually will just be discrete at the most fundamental level. But then that's just as far as it's possible to go. And then what's behind that, like James said, nobody can know then after that, right? But
Yeah.
then maybe that discrete theory will already be sufficient to pretty much make all the predictions in our world that are useful. Yeah.
Then you'd have computational irreducibility, right? It's like you can't simulate everything. Even if you could even if you had the model, you'd have to probably build a computer the size of the universe to make the next prediction, right? Or something along these lines.
Yeah, it doesn't mean that you can predict everything. It's kind of like the nature of time. It's like, but it's predicting the future with some probability, and you want to increase the accuracy of that probability by as much as possible. It's some kind of like Kolmogorov complexity thing. It's impossible to prove that this is the minimal possible compressed size of something, but you can tend towards getting more and more compressed. So there's statements you can make that help with that accuracy. Yeah, and this concept of discrete versus continuous is like one of these eternal debates. I feel that the reason why maybe discrete appeals to us more and why it might be easier for us to reason about these things, or why it could be considered more fundamental from our perspective of as observers like us, is because thinking about the network in our minds with which we think about these things, it's kind of some kind of discrete system. So the neural firings and the way that our thoughts process, it either something fires or doesn't fire. So just like a typical like neural network simulation, there's some kind of like activation function. And I feel like that's what makes things tend towards discreteness as like more fundamental. It's because fundamentally we have discrete notions of stuff that we reason about. So that's just my panpsychist opinion.
Yeah. I mean, I wonder if it's that
Maybe-
simple. You please.
Yeah, I was just going to comment that maybe Occam's razor is just lossless compression, like without losing information. Compress.
Yeah, that's pretty much true. Yeah, I mean, there's a connection between Occam's razor and lossless compression, and also beauty, which you mentioned before, also has something to do with compression, data compression. I mean, Jürgen Schmidhuber has a theory of beauty based on data compression. And what else did you mention before? The unreasonable effectiveness of mathematics also has something to do with Occam's razor.
Can I ask this
Yeah.
question about symmetry and compression? Isn't that like one of the main themes in like when you're compressing things, is like to find symmetries?
Yeah, exactly. Yeah, if something is symmetric, like in the simplest example, if you have like a mirror symmetry, you can just because it's every pattern like appears twice, right? You have to just memorize one side basically of the symmetric image, and then the other side you don't need to memorize. You can just like save some kind of rule which says copy one side to the other side or something like that, and then you need like almost only 50% of the memory or so, and then it's compressed. Yeah, sure. So in that's a simple example, yeah, of how like a symmetry can be used to compress some image. And you can use many other symmetries that appear in images or in music or wherever. And Schmidhuber's theory of beauty, it just says like, yeah, like I think beauty, he defines it as compressibility. Like if something is highly compressible, for example, like these patterns that you see in these slides, maybe like this fractal with a cellular automaton or something like that. That has many little things that repeat themselves, and then that means it's you could compress a lot of it into like a much smaller file size than this image, theoretically, and maybe that's what makes it beautiful then. Yeah.
Yeah, I think it's kind of a mix. You have to have a little bit of chaos, I think. I think though, for some reason, maybe this is a comment about humans, but I think you have to, like, for example, this image, I think the cellular automata would be considered computationally irreducible in some ways, right? Because I think, I'm not sure about that, but, you perform a computer experiment and determine that, and yet it also has a lot of symmetric features. So I wonder, because at some point, if you have too much symmetry, you get to the point of triviality almost, right?
Yeah,
And then
that's
it becomes Yeah.
Yeah, I would have to look up his exact definition of beauty.
Yeah. Because it also symmetry also seems to come in sort of contrast with computational irreducibility in some ways, right? It's like the opposite of that almost.
Right. So I mean that
Yeah.
cellular automata is highly compressible in the sense that when you compress something, you say like, okay, I saw a bunch of bits and repeated elements, so just store the information from one of those elements and then have extra instructions of saying to recreate the thing, take this element and place it in these locations. And you do that for all the different elements that you have, and that's like, how a zip file works, for instance, run length encoding kind of thing.
You're trading time for memory. You're trading memory for time or something along those lines.
Exactly. And so here it's like there's the cellular automata. You could compress it as an image, get a PNG, or approximate it with a JPEG or something like that. You could the Fourier transform of it or something like that, or you could say and what that is like I said, like taking a description of the motifs and a description of where those motifs are located and saying like, here's the instructions for recreating the image. Here it's like basically it's like you could give it the cellular automata instructions as a rule set and say, here's the initial condition. It's very simple. You just have to compute the whole damn thing, and it'll take you have to go step by step.
Yeah.
It means is saying, can one explain more with less, or are we just adding epicycles, so to speak?
So good. Maybe there's a grand futility or circularity, right? I think you could say more with less in a lot of such particular situations, if that eases your existential dread.
I think you could say more using less, but that's interesting because that gets into the definition of information.
Right.
Because if you have less to deal with, then that effectively means the elements with which you're reasoning about contains individually less information. Yeah, so so maybe you can compose. There's more that you can compose that with, there's more complexity that you can create if your initial starting elements are simple. But if your starting elements are very complex, then what you can build with that becomes limited. Maybe just because of like the computational bounded nature of what we have to deal with. Given that we're given a certain computational boundedness, if the building blocks with which you are trying to do stuff in that bounded space is small, there's more unique combinations that you can create. Whereas if the individual building blocks have a lot of information already, I think it limits the amount of states that you can place within that space. So yeah, it's but that is a deep question, Neves.
But also more could just be there's more. If you have more things, then probably there is more noise than relevant information. So
yeah,
it kind of ties into Occam's razor, I guess. If you have like two different ontologies or systems that describe a phenomenon, the one that's more complicated has more moving parts, so to speak, and is like more prone to have errors popping out in it down the line. So it's like, what do you want? Do you want something that's complicated or something simple?
Yeah, it's kind of like the data at the LHC, at the Large Hadron Collider. A lot of it, actually, I think most of it is noise. So they have to go through many layers of filtering and filtering and filtering to get these sort of distilled
what is causing the
events.
noise? Can we talk about that a little bit practically? I think that's an interesting thing I wanted to dig into a little bit too.
Yeah, well, I think, when they're looking for these particular rarities, they have high electromagnetic fields. So, okay, disclosure, I don't actually work at the LHC. I'm doing laser plasma accelerators, but they basically generate many interactions that have a high probability but are of low interest, essentially. So you could imagine all the electromagnetic fields that are generated when you smash bunches of protons together, and most of that sort of passes through the detectors as noise. That's kind of the high level summary. Does that kind of make sense?
It's interesting.
Like
So the detectors are
Mhm.
picking up all kinds of things that are happening during the collision, but what you're trying to sift through is the things that could be identified as some like new particle that spun out in
Yeah,
like some
exactly.
particular pattern or something.
Yeah, like if you see this plot here, the actual interesting result is this tiny bump that shows up in this discovery of the Higgs boson plot here. So you can imagine all these other events around that. This sort of exponentially decaying curve is not super relevant. And yeah, insofar as it's not the signal.
I think the noise comes from like these collisions generating so many particles, like a huge number of particles that fly out, but most of them are not detected, right?
Yeah,
Most of
that
them,
too.
they only is just a small fraction are actually registered by the detectors. So then it makes the data very incomplete, and then they just need a lot of like a huge number of collisions to figure out what's going on. Just like with DNA, it's like that also, I think. If you have like very incomplete DNA, because it's too old or something from a fossil or so, then you need need a lot more material until you can reconstruct the genome, for example, stuff like that. Yeah.
That's an interesting point. So during these collisions, you're not actually picking up all the information. I guess it's impossible to pick up all the information of any one collision. So it has to be like a statistical measure from many, many iterations.
Yeah, precisely. Yeah,
Memes
a lot of
say
the
that Dr. James Balcom, not sure if that's being spelled correctly. He said that before the LHC upgrades, they only recorded 1 out of 40 million events.
Oh, yeah. Yeah, that sounds right. I seem to remember they say when they smash two particle beams together, they only get like 40 events or something. But despite the fact that there's, billions of particles smashing together. So I think that kind of speaks to the rarity of the events. I wish we had an LHC expert here, but this is my understanding.
Can you talk a little bit about your work? That's kind of really interesting as well.
Yeah. So yeah, I'm basically studying. My PhD is how to basically shrink the LHC. So we sort of focus a laser down into a small plasma cell, a small gas cell, and then we accelerate electrons to sort of a fraction of what the LHC can do, but kind of close. In terms of the energy level of these electrons. And with that, you could do things like make an electron-electron collider where you could sort of perform experiments like a tiny LHC, right? Because the size of this laser and plasma, you could fit it into a small garage. So it would be great from a fundamental physics perspective, it would be cool to use that technology to look at nonlinear quantum electrodynamics and try to push the boundaries of fundamental physics on a budget. But I think at this point it's not quite to that level. Yeah.
That's interesting. So this is using plasma to accelerate electrons?
Yeah, precisely. Yeah, you kind of have this very short pulse laser, and it's called the laser Wakefield acceleration. If you look that up, you fire a very short pulse into a plasma, and electrons are sort of accelerated along with this laser pulse. It's pretty cool.
And what happens when you shoot electrons at each other.
Well, yeah, so they haven't built an electron-electron collider yet for this with this technology, but in fact, I'm not aware of like big electron-electron collider facilities in the US or Europe. So I wonder, but I think it's
I wonder if it
similar.
would be useful to do that. As
Right.
far as we know, like electron is indivisible, right? It's just this,
Yeah,
it
yeah.
has no size even that we can detect. It is just
Yeah.
a infinitesimally wide point of negative charge, and it has a little bit of mass, very small amount of mass. So in that regard, I guess like it is more conceivable that you could do this laser thing and get them to accelerate. Because they're not heavy like a proton is.
Yeah, exactly. So in some ways it's more exciting, in some ways it's less exciting. I think they like protons because they get to such they're massive, they get to very high energies. But I think yeah, that there's definitely more to look at when it comes to electrons, of course. I think
Yeah.
there's some recent, I think, study where they supposedly showed that yeah, the electron is in fact a point particle, but I don't know. I have to look at that again. Um,
I wonder if shooting electrons at protons would be beneficial. Like when you smash two protons together, they bust apart with like all these quarks flying everywhere because they're bags of quarks. They have substituent internal components that go flying, and if you could shoot these smaller BBs, so to speak, these electrons at a proton to bust it up without like adding noise to what you get, could be very useful.
yeah, yeah, that would be interesting. May have heard of electron proton collider. I wonder if they have that somewhere. Okay. Any more questions or points to discuss?
Um, but what was the last slide about Plato or Aristotle?
Yeah,
Talking
it's
about the
just kind of a
one.
curiosity.
Mm-hmm.
Yeah, because it kind of reminds me of rheology in some sense. So Plato's Parmenides, and you can see he's kind of going on where you might call a rabbit hole, but
Mm-hmm.
I think he's trying to sort of establish some sort of ontology and well, I guess there's only 18 separate arguments here, so maybe it's not exhaustive, but right, how could you be exhaustive with this kind of language, right? I feel like you'd require something like a cellular automaton or something to be
Well, it's very discrete. Like he's talking about the one, and he's talking about like properties that it could have, and like it's either F or con F, I guess, or not F. It's like he's
right.
thinking about Boolean logic and thinking about like the monad.
Yeah, yeah.
The one is not
Yeah, but
in
then
itself. Yeah,
he talks about partaking of being though, and then it's like, I don't know. I don't know if I lose him or what. I have to But if I recall correctly, he wrote Parmenides later. I don't think it's pseudonymous. I think it's actually attributed to him. And I think he wrote this later in his philosophical career. And I don't know if there was sort of a firm conclusion that work either, or if it was just sort of a exploration.
I like it in a poetic sense. It reads kind of
Yeah, there's definitely
nice, and in a
there's
lot
some
of ways,
poetry.
that's what like philosophy was in that sense, was like sort of oratory, in a way.
Yeah, and that kind of like makes me a little bit irate, you know, like because oratory is generally persuasion, and you think of sort of like shadiness and sleaziness when you think of someone just like trying to convince you of something, right? But in some sense, I think if you use logic, it becomes much more admirable, in my opinion.
But yeah, like as we were talking about, logic sort of this pursuit of something that's simple and beautiful and sort of symmetric and that kind of thing, and this sort of philosophical dialogue is kind of along the same lines.
Yeah, there's a
It
way you
has
could
like
incorporate it.
a
Yeah.
ring of truth to it, kind of thing. That it
Yeah.
has going on. And then this Gödel's God theorem, is this the ontological or
Argue, yeah, you know, I just found this today. I didn't know Gödel, you know, the Kurt Gödel wrote this, but it looks like it's kind of a cute and concise argument here. I didn't actually read it in detail, but
oh yeah, I think it was the property that God is the entity with like the best properties, and
yeah,
if something has a property of not existing versus existing, it's better that that thing would exist in the first place. So therefore, the optimal God must have the property of existence being true for it.
yeah.
But
Is that called the ontological argument? Or is that
I
like
think I remember that being called that.
yeah.
Don't quote me on that though.
Yeah, I might read that again.
Means is saying that an electron ion collider is being built in Brookhaven National Laboratory.
Oh yeah, that's what I recall. Yeah, thanks for reminding me. Yeah, I was there once for a quick experiment. Interesting place.
Awesome. Well,
Yeah, thank you guys for
yeah,
hosting.
thanks for coming on, Joseph, and thanks for everyone joining our live stream. Good questions, good discussions. We'll wrap it up, and we'll see you again next time.
Bye.
Thanks, everyone. Bye.